Hello, my name is Sascha Hanold and I'm working at the Vienna University of Technology in Austria, and I'm going to present the paper on predicting MPI collective communication performance using machine learning. And this is joint work with Abhinav Pateli, George Basilka and Peter Knees. Let's start right with the context. So we are here interested in MPI, in the message passing interface. And MPI is just a specification of a communication interface, and all the communication operations in MPI are defined as functions. So what does MPI cover? So we have point-to-point communication, which is fundamental for communicating in distributed systems. There are also other operations defined for one-sided communications, for example, like MPI put. And there's also other functions for file operations, file I/O, tools are important, MPI data types, derived data types are important, and so on. But what's important in this talk is that we have several MPI libraries out there, like OpenMPI, MWAPIC, MPIC, InterMPI, GrayMPI, and so on. And in this talk, I will focus on collective operations, mainly on blocking collectives, like broadcast, reduce, and all-to-all. And we also look into two specific libraries, which are OpenMPI and IntelMPI. What's important is that we have to distinguish between the semantics of a collective and the implementing algorithm. So the standard defines what a broadcast semantically should do. However, it's not clear how this operation is implemented. There are certain possibilities how to do that. In OpenMPI 4.0.2, there are 9 different broadcast algorithms. So, for example, a very simple linear one. We have a binary tree, and we also have a chain. It is also important to note that each of these algorithms, for example, for a broadcast, may have additional parameters. So, for example, we could have a segment size that we need to set. Or you might apply a k-nomial tree algorithm, and you need to define the number k. And the setting of these parameters, they will strongly impact the performance of the collective operation. So let's take an example here. The chain algorithm has 2 parameters, in OpenMPI at least. So we have a fan out, so how many of these chains we are going to create, and a segment size. So as I said, how large each individual message should be when long messages are split into smaller parts. So what is our problem? So here we take the broadcast example again. So we have a code like this. So here we are broadcasting 100 integers. So what would happen? Let's say we start the application with 256 processes. So we have 16 by 16 processes. And then we have a decision logic that is already fixed in OpenMPI, and it will try to select a suitable algorithm for us. So we go in here and we have a small message size. We are basically getting into this case. We don't need segmentation, and we are using the binomial tree algorithm. However, the best algorithm for a specific case is highly machine dependent. So what we instead want to do, when we call that broadcast here, we jump into the MPI library. The MPI library has some prediction model. It knows these kind of values. This is the feature vector. So we know the collective, that's this one. We know the message size, which is this one. It's 100 ints here. We have the number of nodes and the number of processes per node. We go into our algorithm selection model here, which will be based on some regression models, and it gives us the algorithm ID. So use chain algorithm and the parameters. For example, segment size 1 kilobyte for that specific MPI broadcast call on that machine. Let us show you our approach. So this will be an overview of the entire prediction framework. So it consists basically of three things. First of all, we have some kind of benchmarking task in where we define a set of problem instances for which we want to measure their performance. So for example, a problem could be how fast can an all-gather be done on 16 compute nodes with 8 processes per node and a message size of 128 bytes. And we are going to run this, we are going to test this problem instance with different algorithms that are in there, in OpenMPI for example, and we will generate a performance data set where we have a large table with all the measurements. So we know for all gather, for that specific call here, algorithm 1 on this machine will have a mean running time of 84 microseconds. Once we have that performance data set, we will do some machine learning on that. So we are trying to find the best performing algorithm for a specific case. And once we have that model, we can leverage our model when we are running an MPI program. So when we are MPI program, we are given here our feature vector that is known to us, the collective, the message size, the number of nodes in the process per node. And now our model gives us the algorithm ID for that specific collective. Let's look at the benchmarking first. So what do we need in order to do this prediction? So how would that look like? That's why I give you here a table of the things that we are recording. So that's our feature vector here. We have the broadcast, we have the message size, the number of nodes, the processes per node. We have the algorithm ID. These are the individual algorithms. So for example, algorithm 1 might be the linear algorithm, algorithm 2 might be binomial 1 or binary 1. And depending on the algorithm, we might or might not have certain parameters. For example, here with algorithm 1, it doesn't support segmentation, so segmentation is not available. However, with algorithm 2, we can use segmentation, and we are running our benchmark with different segment sizes. So for example, with 1 kilobyte or 10 kilobyte. And what we are recording is the runtime of each individual case. So how do we build such a data set efficiently? I mean, what kind of parameters do we use? What kind of configurations do we use? So our goal was that we are benchmarking on the most commonly used configuration. The configuration consists of the number of nodes, compute nodes, and the number of processes per node. And we are benchmarking on the most commonly used settings. But there's one catch here. We would like to benchmark in a predictable amount of time. There are certain benchmark suites out there, like the Intel IMB or the OSU micro benchmarks, and they measure for a predefined number of repetitions. So you benchmark, for example, an all-to-all call with some, let's say, medium-sized message for 10 times to get some average, or 20 times. But some of these algorithms on larger instances, for example, you have 1,000 processes, they are really, really slow. Some linear all-gather or some linear all-to-all. And if we are going to do this, the time is eaten up for completely useless cases. So this is not what we want. Our solution is to use the RepRMPI benchmark, which is our own benchmark, but it supports the measurement by predefined time slices. So what we can say is measure broadcast with 100 bytes for exactly 2 seconds. So now we would like to do a prediction. What are we going to do? The feature vector is fairly simple here. And our response variable, that's what we want to predict. We want to do a regression. So we would like to predict the runtime of a specific algorithm for broadcast, for example. what we are going to do is we are going to combine the original algorithm ID, for example, algorithm 1 and OpenMPI and so on, with the respective parameter settings. For example, here, algorithm 2 with segment size 1 will become algorithm 1. So it gets a new algorithm ID, and this will be algorithm ID 1. And the same algorithm with a different segment size will be a different algorithm ID. And for each of these individual algorithm IDs, we build a regression model. Now that we have all these regression models, we're going to do the following. Our input, this is the problem. We have our collective, we have the message size, number of nodes and processes per node. We have that here. And we are querying each individual model. Each model is predicting the runtime of that algorithm for that feature. We are taking all these values, the runtime prediction, and find the algorithm that minimizes the runtime. So with the minimum runtime predicted by any of these algorithms. And our output is then this algorithm ID. And just want to note here again, this algorithm ID encodes two information. It encodes the actual collective algorithm, so for example, linear or chain, binomial tree, and so on. And also, it encodes the parameter settings, segmentation size, fan out, for example. What was our approach then? In order to learn these relationships here. So when we look at this data, we see that the data is not linear. And we, of course, we have experimented with a few learners, random forests, neural networks, and so on and so forth. But it turned out that these GAM models, generalized additive models, and XGBoost were just working well out of the box. We also took KNN, and the intuition here is simple. If you know, for example, a good algorithm for 16 compute nodes, it's likely to work also on 17 compute nodes. But the goal was also take one of these out of the box, apply them usefully, and see whether we can get efficient results. So we were experimenting on 3 different machines. 2 of them, the 2 upper ones here, are machines at the Vienna University of Technology, and the other one here is the SuperMUC NG in Munich. This is the overview of all the data sets. We were looking into broadcast, all reduce, all to all, because all reduce is the most commonly used operation. That's why we are using it here with OpenMPI and InterMPI. And broadcast is interesting because it has many different algorithms. Usually the most algorithms are implemented for broadcast and all reduce. So to test our prediction models, we are splitting into a training data set and a test data set. And we did that differently than, let's say randomly sub-selecting these data sets, because that would not happen in practice. What will happen in practice that we get from Slurm 8 compute nodes, and we benchmark as long as we can. We get 16, we get 30, or whatever the number of resources that we request, and we try to benchmark on as many as we have. Once we have that prediction model, does it actually help in order to improve the algorithm selection? And here we see the normalized running time, and normalized is always to the best case. And this is the blue bar. The best case is the exhaustive search. Since we know the best algorithm for each individual case, that what we have in a data set, we know the minimum runtime for a specific case. Here, for example, for 1 byte of messages and 27 nodes, we know the best running time. And the other 2 bars here don't reach that running time, so they are 25% slower. That's what it means. And the red bar is the default decision logic of OpenMPI, and the green one is our predicted algorithm. So this is the performance. So somehow it predicts the same algorithm as OpenMPI is using already. And we are varying here the number of nodes from here to here, and the number of processes per node. So we use 1 process per node, as we said. then we use 16 processes per node or 32 processes per node. And this one was using the GAM learner. We could have used also the XGBoost, it's pretty similar. But what is important here, that most of the time, the green bar is very similar to the best one, to the blue one. So we are actually finding the best case in many, or we are not far away from the best case in most of these situations here. And in some, for example here, for larger message sizes, we can beat the default decision logic, and quite a bit. So there's a factor here, factor 5. So let's look at int MPI on the same machine, same way of doing things. And again, blue is the best possible. The red one is the one that is selected by int MPI, and the green one is our predictor algorithm. So what we see is that basically the default decision logic is already very close to the best possible. So in general, there's not much to gain, because this is what we have. There are only a few exceptions where we are a bit slower, here for example for that case, than the default logic. But the important thing is here might not look very striking at first glance, but the point is we didn't use any meta information. We don't know how complex the decision logic in MPI is, because we don't have access to that one. However, we are just querying our model that we got from benchmarking, and the benchmarking time is roughly 10 to 12 hours. But then we have that model and we can apply it and instantiate it all the time. So let's see the overall prediction quality. And what we are showing here is some kind of average performance improvement over all the cases. So what we have here, so the baseline is our default decision logic. So coming back to this one, so we are basically looking at the ratio of our prediction and this default. And if we are larger than 1, we have a speed up. If we are smaller than 1, like this one, well, we have a small slowdown. I mean, this is basically 1. This is also basically 1, but it proves the point that there is something smaller than 1 here. And we have these data sets on different machines. Here in orange, we mark the data sets that were recorded with OpenMPI, and these ones are done with int MPI. And we see the performance of these different learners here. So what we see in general, that GAM and XGBoost are basically behaving the same throughout the data sets. KNN in some cases is a bit weaker. And we also see here for int MPI that we are not improving, but we're also not losing, which is a good point somehow, since we have seen that the decision logic in int MPI, it's also an inter-system. So we are using int MPI's library on an inter-omnipath network. I expect them to do a good job on these machines, especially with 60, 36 or 32 compute nodes. So let's sum it up. So what we have been doing in this paper, we proposed a strategy to predict the best possible algorithm for an MPI collective. Our method also takes care of the parameter settings. We have been experimenting with 3 different regression learners, GAM, XGBoost, and KNN, and we did not apply any hyperparameter tuning in order to avoid some kind of overfitting. And our method showed significant improvements compared to default decision logic, especially of OpenMPI. And our method is also on par with the int MPI logic, and right out of the box. And we did not use any algorithmic knowledge here. And what is also important is that the time for building these prediction models is predictable. This is really valuable to know exactly how much compute hours we will consume on a larger compute node, on a larger supercomputer. And last, here's the GitHub link to our repository where we will release the datasets for that paper. Thank you very much for listening.